And you, being diligent students, went home and did it. Oh, I think, did we do 7 together? I think we did 7 together at the end of the class. So y'all tell me about this one. What we need to do in order to describe and sketch the graph of this is figure out what kind of function it is, right? What the parent function or the function type is, because that determines things like the shape and where it lives and all that kind of stuff, how it behaves. So let's start there. How do we do that? Okay, how do you do that? How do you know? Do it. Okay, basically look at what's going on and ignore this and ignore this and see what's left, right? The stuff that we left, right? It's a whole thing. Anyway, the stuff we've been talking about is, okay, what happens if I add 3? What happens if I subtract 2? So if I take those out of it, that's going to tell me what type of function we're looking at. So and I've been calling the parent functions. Just one though. The parent function here would be the square root. What's a square root function look like? Right, yeah. Something like that, right? Sitting at the origin and then just kind of a half little sort of cookie deal going that way, right? Okay. What do these things do to modify that?
Moves it left 3 and down 2.
The +3 is going to shift that to the left 3. And the -2 shifts it down 2. I think we talked briefly, at least at the end of class yesterday, about being careful about the order that you do those in. Again, not quite so important right now, but it will be by the end of class today. So we do want to, sort of work from the inside out. So the +3 would happen first if we were doing the arithmetic. So the thing that the +3 sort of causes in the graph, we want to think about that first, right? So first shift to the left, then down 2. Okay, so where does this end up then? If I take a square root function, shift to the left 3, and then down 2, that point that used to live at the origin would be where? -3, -2. When I ask you to sketch a graph, I'm never going to be grading on, like artistic quality or anything, but kind of capturing sort of the general shape of the thing. And all of these that we've got so far have a good like visual, sort of reference point, right? Like this one, the point where it starts, parabola, that point at the bottom, right? They've all kind of got one point that you can tell apart. That's one that you can keep track of, like where it ends up, right? So it used to be at 0, 0. If I go left 3 and then down 2, it's at -3, -2 now. Okay, cool. And then of course that changes the domain and range as well, right? Those move along with everything else. Oh, so we might as well write them down. What's the domain of this thing, right? The new one, not the original function, but what we're actually looking at. -3 to infinity, yeah, starts at -3 and then it's going to the right. So in the direction of positive infinity. And then for the range, again, same idea, but you want to turn your head sideways and sort of read it like bottom to top, right? So -2 and then the positive infinity. Yep, good. Cool. Okay. All right, does anybody have any questions or anything so far? We feel okay about that? Okay, somebody brought up last class, so just to mention real quick, that you get this kind of, maybe apparently like weird thing about negative values because we are dealing with the square root, right? So if this is our function, if I think about plugging in something that's still in the domain, right? So like -1 maybe. Because we had this whole conversation yesterday about like a square root doesn't know how to deal with negative numbers and that whole thing. this is kind of where the order of operations thing comes back into play. If I plug -1 into this, what do I do first to, simplify or clean things up? The addition here, right? We don't usually write them, but you treat the stuff under a root like it's grouped together, like it's in parentheses. So the first step would be adding these. Well, when I add those, -1 plus 3 is 2. All I really care about for purposes of like the thing working is that that's a positive number. So we're still fine, right? We're still good to go, even though, seeing negatives show up in the domain for a square root maybe gives you kind of a weird feeling at first, right? But it still works out because of the shifts. Okay, cool. All right, how about 9? Different because we're starting from a graph now, right? So we have to identify visually what kind of function it is, and then look for stuff we can keep track of to figure out how it's different, right? How it's moved. So let's start with what type of function this is. Yeah, it's a square, right? And again, that's just from the shape of the thing. This is a square function. Okay, how is this one different from the, sort of basic or default, like y equals x squared? Y equals x squared lives right there. So Noah, you said right 2 and down 3. How can you tell? Yeah. Yeah. Again, this is where it's nice to have, a point that we can kind of focus on, right? To look at. It used to be right here at 0, 0. Now that same point, it's called the vertex if you care. If you don't, then you can wait a month or so to care about it being called the vertex. But that point used to be at 0, 0. Now it's at 2, -3. So that's 2 this way to the right and then 3 down. Right, to end up at 2, -3. So how do I take a square function and force it to go right 2 and down 3? -2 where?
It would be -2
inside of the square, right? Yeah, so we're basically like filling in, right? I've got a thing that looks like x squared, but possibly with something extra in here, possibly with something extra out here. So the 2 to the right should happen on the inside.
And then the -2.
It's got to be minus to move to the right, and then -3 on the outside. Now, the last one, we could have started by just going right to a calculator and graphing, right? This one I can't because I'm starting with a picture, right? I don't know how to type in a picture, but I could, once I think I have something that works, then go and graph it, right? So if I'm, maybe not sure about this, I could say, okay, what does y equals x -2 squared -3 look like? Is that what I was trying to get? Yeah, that looks good. So, okay, cool. I feel good then, right? If I made, one of the kind of simple mistakes that can happen, like putting the wrong sign somewhere, I think that's my answer. I look at this, I go, oh no, that's not right. But I know how to fix it because what's wrong about it? It moved that way instead of that way. So go to the thing that did that, right? Which is that 2 on the inside, and take the opposite sign because you want it to go the opposite way, right? Okay, so, you can use that as a way to check, and hopefully, you're kind of in the ballpark enough that you can figure out where you went wrong and fix it, right? All right, and then the last one, we're just going to write it down. It's an absolute value. So again, I'm just kind of filling in, anything that might be missing there or there. We want it to go up 2 and to the left 6. X plus 6 plus 2. Yep. And then again, I could check and make sure that it does what I wanted it to do, right? Okay. We all feel, mostly okay about that? Like we're on the same page? Okay, right on. Okay, so that's what happens if you add or subtract either sort of to the x value or the input or the argument, like inside the parentheses, right? Before the function does its thing. That's a shift to the left or to the right. And again, feels kind of backwards. Or if you do it afterwards, right? After whatever the function does happens, then you kind of impact the y values directly and you shift up or down, and that one, feels a little more natural. So that covers basically every possible way that I can take a function that I know about and add or subtract something to it, right? Either I do it before the function thing happens or I do it after, but we've looked at both now. Today, we're going to look at another kind of, sort of like minor change, right? But instead of addition or subtraction, we're going to look at what happens when I multiply. So kind of broken it down into a couple of different things here. What happens if I multiply in a way that changes the sign, right? So multiply by a negative. Or what happens if I multiply by, a constant? If I multiply by 2 or 5 or a half or whatever. Pretty much, the same kind of pattern we looked at yesterday. So I'm going to start with, I put a graph together in Desmos. You can scan that QR code to pull it up. And then it's going to have basically each of these three things kind of built in. And what I want you to do is take a couple of minutes and just kind of, fiddle around with things on your own a little bit and try to get a sense for what's going on. And then, I'll, keep you posted on when I want you to, well, whatever, do it whenever you want, but talk to people around you and, see if they agree, try explaining it to someone. You have to think about things differently to be able to tell somebody else about it. So take a couple minutes to kind of figure out what's going on for yourself and then try to explain it to somebody and, see what you agree on or maybe don't. We'll all reconvene in a few. Okay, so we've got a parent function in here. It doesn't really matter what, but it's the square root function, that red dashed line. That's going to stay there just as kind of a reference so we can see what's going on. And then we're looking at first, what happens if I take that and throw a negative sign out in front of the whole thing? Negative square root of x. Okay, well, we've had a chance to talk about what changing the sign of something does a few times in the last couple of days. If you look at like 2 and -2, right? How are they related or similar and how are they different? Okay, number and it's negative. They have the same absolute value. They have the same absolute value. And absolute value tells you about how far, right? It's distance. So they're the same distance from 0, but in opposite directions. Okay, so negatives are tied to direction and to oppositeness. I don't know if that's the word, or any word. So what does this negative absolute value, or whatever it is, square root of x, what does that do? It's a reflection, and I kind of gave you the word reflection, but what does reflecting mean? Like, what do we mean when we say something is a reflection? Mirrored, yeah.
It's the exact same function, but just in a different direction.
Same thing, but in a different direction. And we might even be more specific about the different part. The same, but in the opposite direction, right? Just opposite in a like specific way. Okay, so the reflection part is that we're mirroring, we're flipping, we're taking the opposite direction. And Lauren, I think you also said something about, sort of clarifying the opposite in what way?
All the y values are negative.
All the y values are negative now where they were positive before, right? Or again, all the y values are the opposite of what they were before. So that reflection is relative to what then? Like in what sense are we flipping or mirroring? Over the x-axis. The x-axis is the thing that stays put. And that's because this negative sign out in front, that's going to flip the sign on all the y values. And the only one in the whole wide universe that doesn't change would be 0. -0 is just 0, right? That's the only thing that doesn't have an opposite. So it's a reflection, meaning mirroring or flipping, over relative to the x-axis. X-axis stays where it is, everything else flips. reflection. Like imagine that all the letters are in there over the x-axis. Where does just to tie things back into yesterday, because I said the words inside and outside about 1,000 times, right? Where is the sign change? Where's the negative here? On the outside. What does outside stuff do? Think about, shifts and stuff. Changes the y values, right? It affects the y value, moves up and down if you add or subtract. This negative is on the outside. There's an exclamation point. It's on the outside, and it reflects or flips which way? The y values, right? Over the x-axis. The x-axis stays put, but that means we're flipping it upside down. So again, it's changing things from the perspective of y, right? We have to say it reflects over the x-axis because that's what stays put, but that means it's flipping upside down. Okay. What probably happens then? I mean, you've seen it already, but what probably happens with the other one? It affects the x values because it happens on the inside. So it's going to reflect or flip, only now it's going this way, left and right, which means it's reflecting over the y-axis. If you want to think about it as opposites and individual values and stuff, now we're taking the opposite of the x values. Okay, instead of being a 2, you're at -2 now, right? Or whatever. That means that the y-axis stays put because what are all the x values on the y-axis? Like what do points on the y-axis look like? Oh, no. Okay, sorry, it won't let me pull up the point, but like, what are the coordinates of this point? 0, -5. That's why the y-axis stays put because, taking its opposite doesn't move it at all. So y-axis stays put, we flip it this way, I get this thing that faces now instead of, sort of starting at 0 and going off to the right, it comes in from the left and then stops at 0. All right, so it's going to flip the domain around as well. Okay, so it's a reflection over the y-axis, which means it's flipping left and right. Right, it's backwards in a sense. Okay. Make these lists look the same. Here, the opposite, the sign change, the multiplication by a negative is happening on the inside, and again, it affects things, from X's perspective, from the left-right perspective. Okay, everybody good so far? Do you have any questions, worries, doubts? Don't see any furrowed eyebrows or anything. Okay. All right. What if we multiply by something other than 1, right? Here we're multiplying by -1 somewhere. The negative part gives you the opposite. What if I multiply by 2?
Stretches.
The graph stretches. Okay. Stretches and what's in?
The x value is at 1, now it's, the y value is at 2 now, because it's getting multiplied.
Okay. So you're focusing on like a single point. That's a good place to start.
1, 1.
At 1,
Moving up to
square root of 1 is 1, so 1, 1, right? On the original thing. Only now I'm taking the square root of 1, which is still 1, but I'm multiplying by 2. I'm doubling it. So now instead of 1, 1, I've got a point of 1, 2. Every other point on here, whether it's got pretty coordinates or not, the same thing's happening, right? I'm letting the function do its thing, right? Think order of operations again. Square root counts as an exponent, so that happens early, right? Square root does its thing, that gives me the shape, but then I take all the y values, because this is inside or outside? Outside. That's outside. So I take all the y values and I double, right? This is multiplication, and it's outside. So the shape of the function stuff is determined, and then I make all the y values twice as big. Well, okay, of course it's going to sit higher then, right? So one way, another way you can think about this or kind of view what's happening. Take the graph that's on the outside, so it should affect y values, right? Up and down. Take the graph and imagine it's on like a big sheet of like silly putty or like stretchy rubber or something. Because it's happening outside, I want to change y, so I'm going to hold the graph by the top and bottom and stretch it out this way. Right? That's kind of what we mean when we say stretch. If I take this graph and stretch it this way, what happens is that it pulls up like that, right? So this purple graph, that's 2 times the square root of x. That's taller, faster. Somebody in the last class said sharper, I think, steeper, right? Like these are all words you could use to describe how that compares to the original thing. It's stretched, but it's stretched vertically so that it sits up higher, right? Everything happens faster, it's steeper. Okay, what if instead of 2, that was a half? Instead of stretching it and making it taller, same idea, you hold it by the top and bottom because it's still a y value thing. Only now you compress it down, you squish it in, you shrink it. Well, that's going to make the graph go that way, right? Kind of closer into the x-axis. So if I multiply by a constant like that, and sometimes that's called a scaling factor or scaling the thing, what that's going to do is either stretch it out and make it sort of sit taller if that number is bigger than 1, or it's going to shrink it down and sort of make it like shorter, slower, wider if you want, if that number is smaller than 1. Okay? Okay. So multiplication is all about changing either direction, if we're changing the sign also, or the shape a little bit in the sense that it's, taller or shorter, kind of, right? Faster or slower. Okay, so addition, subtraction, move things around. Multiplication then can flip, or it can sort of stretch and shrink. And that's everything. And again, it's all, you can think of it all consistently as things happening inside affect things left and right because they change the x values. Things happening outside affect things up and down because they change the y values. Okay. All right, so y'all take a couple of minutes and think through, a couple of these. I don't know, maybe take a look at those 2 or something. Mm-hmm.
And I apologize for being late again. Somebody wiped out on 5.6 again.
It's the way of things.
I'm gonna start going the other way.
Yeah. Once you, kind of thought about it and feel good about things, of course, check somehow if you haven't, graph it in Desmos or in a calculator and see if it lines up with what you expected. And then again, talk to a couple people around you and see if y'all agree. All right, what do we think y equals 3x squared ought to look like? X squared, so that, right, general shape. but then stretched by a factor of 3. So what is that gonna look like? How's that gonna compare? So it's stretched because that 3 is happening outside of the square, right? Sort of out in front. If I'm thinking order, the square happens first, then times 3, that's outside. That happens after whatever the function is doing. So it's going to be stretched by 3, but it's going to be stretched this way. So instead of being sort of wider, that's going to make the whole thing kind of narrower, steeper. There it is. So it sort of sits, inside of x squared because it's taller, right? The individual points, like x squared goes through 1, 1. This would go through 1, 3, because you take that y value and multiply by 3, right? So it sits higher up, or steeper, or faster, or skinnier, or whatever. This one that I didn't ask you to do, but multiplying by 1/3 instead, that's going to be sort of wider, right? It's going to shrink down vertically. So sort of compress it out and the whole thing kind of like lays out, right? So this would be, narrow or skinny or whatever, right? It's a stretch vertically by a factor of 3. This is going to be wider because it's shrink, stretch. I guess I'm saying it in present tense. I don't know why I'm worrying about verb tense here, but what can you do? By a factor of 3. So instead of hitting 1, 1, it's going to hit like 1, 1/3, right? Because it's shrunk down, so the whole thing's kind of laying out and slower, right? Wider. I didn't mention, but I should. We didn't talk about what happens if you multiply by something by a constant on the inside of what the function does. What do you think happens? It's a stretching, shrinking thing, only this way instead. And that is what happens. We're going to just kind of sidestep this and pretend like it doesn't exist for a couple of reasons. One is that this works kind of backwards of what you expect. And 2 is that for the graphs that we have, like think about, x squared. If I grab that by the top and bottom and stretch it this way, then the whole graph gets steeper and more narrow, right? If I take that same graph that I started with and grab it this way and compress it in instead, what does it do? It gets steeper, more narrow, right? So I can't distinguish by looking at it which of those is happening, right? If it's this way, or this way, I can't tell the difference. And the same thing's pretty much true for all of these function types that we have. And also, if you've got both of them happening and everything kind of mixed together, it all just ends up being like a little bit extra, like it's just kind of too much. So we're not going to do any horizontal stretching, shrinking stuff. I've chosen homework questions where it just doesn't happen to come up. Oh shucks, right? It does, kind of work the way you expect it to, but we got to be careful with it. And again, I can't really tell the difference. If you go on to pre-cal, you'll hit this idea again with trig functions. Trig functions kind of oscillate. It's like a wave shape kind of thing. So there you can tell the difference between going this way and going this way because of the shape. So you guys that go on to pre-cal, you'll kind of revisit that idea there. If you're not, then you don't care anyway, probably. And like I just took something out of what we have to worry about, right? So any stretching, shrinking stuff we do is always going to be vertically. Okay. All right. Now, the one other thing that we have to worry about is that the order is important here. I kind of mentioned this yesterday and earlier today. If all you're doing is shifting around, it doesn't matter so much because you end up in the same place anyway. But if we do more than one thing, you do the y-axis for me. If that's a y-axis, if I take x squared, if I shift it this way, which is to the right for you, but to the left for me, that's confusing. If I reflect over the y-axis, then where do we end up? If the y-axis stays put, right? If Jamel doesn't move, then I go from over here to over here when I reflect, right? Well, what happens if I reflect over the y-axis and then shift to the right? End up over here. So this and this are not the same, right? So one of those is correct, one of them is not, thank you. So especially when we've got multiple things happening in kind of the same direction like that, we have to be really careful about the order. Because you can end up with different things. Where did I put? I gotta like tie this onto me or something. It's harder to tell sometimes though, like when I really need to worry about it and when I don't so much. So we're always just going to assume that it does matter, assume that it is important. It matters. The way that you can deal with it though, is just pay attention to order of operations, right? Just do stuff in the same order you do the arithmetic and everything kind of takes care of itself. So if I look at this, for example, first of all, what kind of function is it? A cube. So looks like that, right? It's a cubic function. Now, if I'm going to think about all the stuff that happens to it, what happens first? That, right? If I give you an X value to plug into this and say like, tell me what the Y is that goes with it, right? Just do the arithmetic. The first thing you would do is this, X plus 2. So the first thing I do in terms of transformations and changing the graph and stuff is whatever that says to do. I should write things down. So the parent function is x cubed. The first thing I want to do in terms of changing the graph is whatever this does. One more time, that x plus 2 would move it to the left too. Left has a t in it. Shift to the left too. Okay. Then what? Then again, if we're thinking like order of operations, then the cube would happen. Right? That would be the next thing because the exponent. Okay, that tells you what the shape is. After that, then we're talking about stuff that's happening outside. Right? Once we do whatever the function does, we've moved from the looking at the inside and looking at the outside. So what's the next thing that happens? Times 5. What does that times 5 do? It's multiplication, so it's going to stretch the graph out, right? That's going to make the whole thing taller, steeper, skinnier, more narrow, like whatever, right? I'm just going to write that that's a vertical stretch by a factor of 5. So if a point was at 1 before, now it's at 5. All right, if it was at 10 before, now it's at 50. Okay, so we've taken care of this and this. What's left? The -1. What does that do? Shifts the whole thing down 1. Okay. What does that look like? Let's say there's original, classic flavor, x cubed. We need to move left 2. Cube's a little bit harder because this point doesn't stand out quite as much, but like that one where it kind of shifts over, I can still keep track of where it goes. Where is that point that used to be at 0, 0 going to end up? -2, -1. Right, left 2 and then down 1. Let's say that's -2, -1. Okay, and then if I'm gonna draw the graph, how should it look compared to the original thing? We could actually like find points if we needed to, like I could plug in 0 or something and actually figure out what it is. Five times 0 plus 2 cubed minus 1. So that's 5 times 2 cubed. That's 5 times 8. So 39, right? Like that would be an actual point. But in general, how should it look compared to the original thing if we stretched it vertically by 5 times? This way or this way? It should be taller, skinnier, right? Sharper, faster, whatever. So I'm just gonna, oh crud. Try that again. Something like that, right? Kind of the same shape, but again, like taller, narrower, or whatever. It's still kind of got the curvature to it. I didn't do the best job drawing it. But everything happens faster. Okay. Do you have any questions about that? Does that all kind of make sense? This is a thing that, you know, is probably not really going to click all the way until you do problems. So there are, I've got just the thing for that. There are 4 here that we haven't talked about. Try these. When we get back together, whenever that is, hang on.